Okay, in the previous discussion, we were looking at conditional CMFs and CDFs. And so the remaining topic then is the cumulative conditional CMFs and CDFs. Okay, so if you're talking about probability of x given some information about y, well, what's the probability that x takes values from minus infinity to some value given that y has taken some value? Okay, so that's what we're looking at now. Okay, so we start with the definition of a cumulative PMF. So you have discrete random variables x and y, and before, if you wrote small x given y, right? And then what you were saying is, and then a given b, that would have, with the small f, that would have meant the conditional PMF, right? The idea of that, what's the probability that x is equal to a given that y is equal to b? But here, we're writing a capital F. By that, we mean the cumulative conditional mass function. Okay? And that means that what's the probability that x is taking values less than or equal to a given that y has taken the value b? Okay? The probability that x is less than or equal to a given that y is less than or equal to b, that's what this thing is defined to be on the left, right? Okay, so what do? If you already have the conditional PMF for x and y, right? What's this? This here. This is the probability that x is taking the value small x given that y is taking the value small b. You sum all of those possible x's which are less than or equal to a, and then that is the cumulative conditional mass function. Okay? So you get it by summing the conditional mass function. Okay? What do you think would happen if you had you had continuous x and y, and you were looking at, right? This would be replaced by an integral from minus infinity to a. Okay. All right. So let's think about this one. You have two fair die. One is red. The second one is blue. We do one roll of both dice. X is the result from both dice. Y is the result only of the red die. Okay. So let's see. X is both. Y is red. And I'm asked for the value of that the cumulative conditional mass function gives. With this input, 7 given 4. So what does this mean? This notation means that y is definitely equal to 4, right? So what's the probability that x is taking values less than or equal to 7? And what's x? X is the result of both die. So y has been set equal to 4. What's the probability that both die are giving a value less than or equal to 7? Okay, so what could x be? Okay, the other die could, you rolled, with one die you rolled a 4. With the other die you could roll a 1. That would give you a total of 5. With the other die you could roll a 2, and then 2 plus 4 would give you 6. With the other, with one die rolling a 4, you could roll a 3 with the other die, and that would give you 7. And, well, okay, so the values that you could, given that the red die gave a 4, the total could be, which are less than or equal to 7, could be 5, 6, and 7. Okay? So, and this is the result of rolling 1 with the other die, 2 with the other die, and 3 with the other die. Okay? So, how do you work out the probability? This is the probability of rolling a 1 with the other die, plus the probability of rolling a 2 with the other die, plus the probability of rolling a 3 with the other die. Okay, so what's, right? So with the other die, the probability of rolling a 1 is 1/6, a 2 is 1/6, and 3 is 1/6. So that should give you 3/6. Okay, and so look at it this way. X less than or equal to 7. The conditional probability mass function rolling an x, rolling the value total value of x, given that the red die has given you a 7, right? So this is sorry. What am I? Sorry, 4, right? Okay. So this is the conditional evaluated at 5 given 4 plus the conditional evaluated at 6 given 4 plus the conditional evaluated at 7 given 4. Okay. Plus the probability of the other die rolling a 2, plus the probability of the other die giving a 3. Each of those is 1/6. Maybe I should, right, fair die, 3/6. Okay. All right, so that's an example of using the cumulative conditional probability mass function. Okay. Now, if we have, in that case, we had 2 discrete random variables. So they had a conditional PMF and a cumulative conditional PMF. Now, if you've got continuous x and continuous y, so each one has its own PDF, right? And then you have its conditional PDF, which is the probability density, not the probability, the probability density for x given y. And then if you want the cumulative conditional probability, right? This notation means the probability that x is less than or equal to a, given that y is definitely equal to b. So you take the conditional PDF for x given y. The y is fixed at b, and x is ranging from x is taking values from minus infinity to a. So let's say we could call that t, and so t is going to take values from minus infinity to a, right? And that gives us this thing there. Okay, so that was this was the material that was left over from the previous session. And then there are some exercises that you should do on your own for the for this conditional probability idea. Okay. 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 Then we go on to moment generating functions. Okay. So we've already done with moments. I may not have used the word, but we've already talked about moments. So the expectation of x is the first moment of x. When we did variance, we needed the expectation of x squared. The expectation of x squared is the second moment of x. Now, we won't always be, in this course, we're not going to really discuss the other moments, like expectation of k would be the kth moment of x. But if you do another probability course or another statistics course, then the higher moments become important, right? So moment generating functions are a way of algebraically extracting moments of functions and avoiding doing the summations or the integrations, which can be challenging, right? So moment generating functions are a way of generating all the moments of a random variable, okay? And doing it in an algebraic manner rather than using summations or calculus. Okay? So, this is it. The expectation of x to the n is the nth moment of x. We've already talked about the expectation of x, the first moment, and the expectation of x squared when we were talking about variances. Okay, but if you want, if you do further discussion of probability and of statistics, then we also talk about skewness and kurtosis, and they would require the calculation of fourth moments, for example. Right? So, turns out that moment generating functions can give us a way of extracting moments in an algebraic manner, which is sometimes easier than doing the direct integrals and sums that we've had. Okay? All right. Generating functions in general are formal power series, and within that power series there's some way of encoding some information that you like, and then you do algebraic manipulations on that to get out the information that you want. Okay, in general. Right? And in our particular case, we're looking at extracting moments. So, I'd like you to, we're going to be using this a number of times. So I'd like you to recall the Taylor series for the exponential function, or e to the x. If you want to write it as an infinite series, you can write it like this, right? 1 plus x over 1 factorial plus x squared over 2 factorial plus x3 over 3 factorial, and so on and so forth. You can write it as this infinite degree polynomial, or this infinite series. Okay? Hopefully you saw that in calculus 2. If you didn't do calculus 2, then, well, now you know. Okay? This you'll need to know, yes. Yeah. Okay. All right. So the idea is if you want to, so for any real number, if you wanted to know what e to the x is, or what the exponential of x is, you'd put in that value of x, and you'd sum up all these infinitely many terms, and it would give you the exponential of x. Okay? All right. Now we define the moment generating function. All right? Remember we talked about expectations of a random variable, variances of a random variable, and so on and so forth. So I have a random variable x, and what I do is I take my function of x is exponential of tx. Okay? So I had a random variable x. I invented a new random variable, exponential of tx. Now I calculate the expectation of this new random variable. I call that and when I do this, when I calculate the expectation, I'm supposed to be doing either a sum or an integral. So I'm going to sum out, or I'm going to integrate out all the x's, and what I'm going to be left with is a function of t. Once I do this, I'm going to be left with a function of t. And that function of t, I write as m sub x of t, and that is the moment generating function of x. Okay? Okay, so far that's just formalism, but we'll see in a bit how I can then use the moment generating function to find the moments of x. Okay? But for now, let's say this is just a definition. Okay? Okay, now this e to the tx, right? So e to the tx is what? E to the tx is this infinite series. Well, it's either, if you know how to calculate e to the tx, that's fine, right? You replace x by tx in here. If you can calculate e to the tx on your calculator, all right. But in principle, it is this infinite series. Okay? Now, infinite series, sometimes they diverge off to infinity, and sometimes they converge. Right? So you will, even if you didn't do calculus 2, you've seen the geometric series, right? Right? So the geometric series converges for some values of x, right? 1 over 1 minus x is equal to 1 plus x squared plus x cubed. That's the geometric series, right? So that converges for some values of x, and it diverges for some values of x, right? So it doesn't converge for x is equal to 1, for example. So when you're dealing with an infinite series, you might have sometimes What does it remind you of? Oh, okay, look. If I call this P 1/5, and I called it, well, that's 1 minus P. I could call that Q. So if P is 1/5, that would be P e to the t plus Q, and I could call N 100. Okay. Oh. But if I had a binomial random variable with parameter n equals 100 and p is 1/5, and I calculated its MGF, I would get this MGF. So I might suspect that x is the binomial random variable with the parameter p is 1/5 and n is 100. Could another random variable of a different type, not of the family of binomial random variables, well, it turns out that there's a uniqueness theorem which says that no. So this random variable, for which this is the MGF, is in fact the binomial random variable with parameter p equals 1/5 and n equals 100. Okay. Okay, so okay. For the geometric random variable, this is the MGF. And if you were working with some random variable and it turned out that this is what its MGF was, you would say, okay, that random variable must be the geometric random variable with this parameter p. Okay, and again. Okay, Poisson random variable, again, it's a non-trivial business. But eventually we get this. The Poisson random variable with the parameter lambda has an MGF exponential lambda e to the t minus 1. Okay? So if you find that the random variable you're working with has this MGF, then you will immediately say that the random variable is a Poisson random variable with parameter lambda. Okay? And again, you can extract the expectation and the variances that we already had. Now, sometimes we would want to consider things like, what if I had two independent random variables, and then I make a new random variable by adding them, or by a scalar multiple, or by adding a constant. Well, it turns out that we can get some rules for that. So if we already know the MGF for x, and we invent a new random variable y equals x plus a, then, okay, the MGF for y as a function of t is the expectation of e to the ty. What's y? Replace y by x plus a. So it's the expectation of e to the tx plus ta. Okay, well, this expectation will be a sum over x's or an integral over x's, right? So e to the ta is a constant, so you can pull e to the ta outside. Oh, well, this is just the MGF for x. Okay? So the MGF for x plus a constant a is e to the ta times the MGF for x. Okay? Well, what if we have a scalar multiple? The y is bx. So the MGF for y is the expectation of e to the ty. Replace y by bx. So it's the expectation of e to the tbx. Okay? Well, we can think of tb as another constant. Right? T was a constant, b was a constant. Okay? So this is the expectation, this is the MGF for x with t replaced by tb. So everywhere, so if you knew the MGF for x as a function of t, and you want the MGF for b times x, b is a constant, then just take the MGF for x and replace t by bt, and there you have it. So, okay, so I've got m sub x of t is equal to expectation of e to the tx, right? So m sub x of, let's say, 2t is expectation of e to the 2tx. Okay? Yeah, so that's what I'm saying there. All right. Okay, sometimes we're going to need to standardize our random variables, right? So what we do is, if we have our random variable x, if we subtract off its expectation and we divide its standard deviation, then we get a new standard random variable, let's say x hat. And this has the property that its expectation is 0 and its standard deviation is 1. So this is called normalizing or standardizing the variable. Okay? So what's the MGF for the standardized x? Right? Well, we applied the previous two rules. Right? We applied the rule for adding a constant, and we applied the rule for multiplying by 1 over sigma. Right? So if we apply those two rules, then we get that the MGF for the standardized variable is the MGF for the old variable with t evaluated at t over sigma rather than evaluated at t, and multiplied by e to the minus mu t over sigma. Okay, so that's something that can often be useful. And another big rule. Yeah.
Why did we divide it by sigma?
Oh, because we're multiplying by 1 over sigma. So another big rule. Remember, if you have independent random variables, their joint PDF. So you have two independent random variables, x and y. You're going to add them together. Okay? Then their joint random variable, because they're independent, their joint PMF, sorry, is the product of the individual marginal PMFs. We saw this before. Okay? So let z be the sum x plus y. So then the MGF for z is expectation of e to the tz. But tz can be replaced by tx plus ty. Oh, now, because these are independent, right, this can be replaced as e to the tx times e to the ty. There won't be any problem there. Okay? And your xy here, your joint PMF, can be replaced by the products of the individual marginal PMFs. Okay? So now you're doing a double sum over x and y. Well, just do the sum over y first, let's say, and the sum over x first. And what do you, right? And then what you're left with is the product of the two. Okay? So if x and y are independent, not if they're, if x plus y with x and y independent, then the MGF for x plus y is the MGF of x times the MGF of y. Right? Yeah. The MGF of the sum x plus y is equal to the MGF of x times the MGF of y, but that depends upon x and y being independent random variables. Okay, as I said, the uniqueness theorem, two different types of random variables don't have the same MGF, right? So you can, the MGF allows you to identify the random variable. Okay? All right, so like I said, this one is for what kind of random variable? Binomial with p equals 1/3, n is equal to 5. Okay? All right. What about this one? Right. What about this one? Okay. That's right. For the Poisson, it's exponential lambda e to the t minus 1. Okay. Okay. Sum of independent binomial random variables. Okay. So z equals x plus y. X and y are independent. This has parameters mp. This has parameters n and p. So what are you going to get? Well, this was the binomial, right? With parameter m and p. This is the binomial, the MGF for the binomial random variable with parameters p and n. This is for p and m. What's the MGF for the sum? Is their product? Okay, the product goes like that. Okay. So z is another binomial random variable with parameters p and m plus n. Okay? All right. I'm not sure whether we have a class on Thursday or not. But okay, then if we don't, then I'll see you next week.